A vector database is a specialized system designed to store and retrieve vector embeddings, which are numerical representations of data like text, images, and audio in a high-dimensional space. These vectors capture semantic relationships and features of the data, which are essential for tasks like similarity search, recommendation systems, and other AI-driven applications. In short, vector databases help us store data in a way that makes it easy to find similar data points using advanced indexing techniques. A vector is a list of numbers, also called embeddings, that represent data points. The key point is that vectors capture complex relationships within the data, such as the meaning of a sentence or the features of an image in a high-dimensional space. For example, in NLP, a sentence like "the cat is on the mat" might be converted into a vector using a model like BERT. The resulting vector represents the meaning of that sentence in a mathematical form, which allows for comparisons between sentences based on their semantic similarity. In a vector database, each data point, for example, a document, image, or audio file, is represented as a vector in a high-dimensional space, and similar data points are placed close together while dissimilar data points are placed farther apart. This allows the system to perform similarity searches, which are core to the database's function. For example, if you query the database with a vector representing dog, the system should return vectors representing puppy or pet, which are semantically similar. So what is similarity search and indexing? To perform similarity searches efficiently over large datasets, vector databases use indexing techniques. Indexing allows the system to quickly find the closest vectors to a query without comparing to every single vector in the database. The most common indexing methods include approximate nearest neighbor or ANN algorithms, which reduce the search space for efficiency. So what is a search index? A search index is a data structure that organizes vectors in such a way that the system can quickly find similar vectors without doing a full comparison. Think of an index like a map or a shortcut that speeds up the process of searching through high-dimensional data. Without an index, the system would have to compare the query vector to every other vector in the database, which would be very slow, especially with large datasets. Let's talk about some indexing techniques in vector databases. Firstly, inverted file indexing. In traditional text search engines, an inverted index maps terms to documents that contain them. It's useful for finding documents that contain specific keywords, but how does this apply to vector databases? In the case of vector databases, the inverted index can still help by mapping features or dimensions of vectors to the data points that contain them. Instead of searching for exact terms, the database indexes the vector features that are important for similarity comparisons. This makes similarity search much faster, as the system can avoid searching through all the data and focus on relevant features or dimensions. For example, if two vectors share a similar feature, like a specific value in one of their dimensions, the inverted index can help identify them without checking all the vectors in the dataset. Secondly, randomized trees. A well-known algorithm for approximate nearest neighbor search is Annoy, which stands for approximate nearest neighbors, oh yeah. It uses randomized trees to partition the vector space. In Annoy, the vector space is recursively split into two parts by creating random decision boundaries or hyperplanes that divide the space. These splits are stored as trees. The key idea is that by organizing the vector into these trees, the database can search through them more efficiently. Instead of comparing the query vector to every other vector in the dataset, Annoy searches through the tree structure and finds the closest vectors much faster. So why randomized trees? The use of randomized hyperplanes or decision boundaries makes it faster to build the trees and allows the database to quickly approximate which regions of the vector space contain the most similar vectors to the query. Now let's talk about HNSW graphs, which stands for Hierarchical Navigable Small World Graphs. HNSW is another popular indexing technique that organizes vectors into a graph-based structure. In this approach, the space is organized into multiple levels, like a multi-layered graph, where each layer contains a subset of vectors. So how does this work? Vectors are first inserted into a hierarchical graph structure where each vector is connected to its closest neighbors. The higher layers of the graph are sparser, and lower layers contain more vectors, making the search more efficient as you navigate from the top layer down to the lower layers. When performing a search, the system navigates through this multi-layer graph to quickly identify the closest vectors. HNSW performs extremely well in practice because it allows the system to quickly navigate through the graph and find the nearest neighbors. It also adapts to the data distribution. There is very quick navigation through proximity links. HNSW creates shortcuts between vectors that are likely to be neighbors, which significantly reduces the search path. This graph structure allows the algorithm to make larger leaps in the sparse upper layers, avoiding the need to check every vector at every level. It also adapts to the data distribution. Unlike fixed partitioning methods, HNSW dynamically builds a graph that adjusts to the dataset's distribution. This adaptability means the graph naturally groups similar data points, reducing unnecessary comparisons and allowing for more accurate and efficient searches. But how do we actually determine how close two vectors are? We need a distance metric. There's a couple common distance metrics that are used in vector databases. Cosine similarity measures the cosine of the angle between two vectors, and it's particularly useful in NLP tasks. Euclidean distance measures the straight line distance between two vectors, and it's widely used in image retrieval and numerical data. Manhattan distance is the sum of the absolute differences, and it's used in certain clustering tasks. As the amount of data grows, vector databases have to scale efficiently to handle millions or even billions of vectors. There's a couple ways that vector databases achieve this scalability. First is sharding, in which the data is split across multiple machines or servers to distribute the load and make searches faster. Second is replication, in which copies of the data are maintained on different servers to ensure fault tolerance and availability. If you enjoyed this breakdown and found it helpful, don't forget to like, comment, and subscribe to stay updated with more coding and tech deep dives. And if you'd like to support my work, you can buy me a coffee through the PayPal link in the description. Thank you for watching, and see you in the next video.